Hello everyone, welcome back to the final part of lecture number 3, and now we're going to talk about expected shortfall. So far we've talked about value at risk. So what is the level of losses that won't be exceeded a certain percentage of the time? And now expected shortfall is, hey, what if we exceed this value at risk level? So if we exceed this boundary, then what will our losses be? So this tells you more about, hey, what do you really expect to lose as soon as you actually make losses, rather than tells you something about, hey, what losses will we not reach with a certain certainty. So if you want to estimate this from historical data, you can do that very similarly to the way we did it before. You start by sorting the losses and then look at, hey, if my value at risk is at a certain loss, what are my losses once those are exceeded? So you look for, so suppose your value at risk is at the 10th biggest loss, then look for the losses that are even bigger than that. So that's losses 1 through 9, and then take the average of those values, because that's your expectation. So in order to show you this, to get a bit more of a hands-on feeling for this, let's take the example we had before. When we calculated the value at risk, suppose we have 1 year of data, so 252 data points that were part of a certain histogram of returns. If we then sorted all those observations, we found this data. Here we have the biggest losses from loss number 1, and then the 20th biggest loss here is loss number 20. Then we found that the value at risk for 1 day at 99% for a $100 million portfolio was 18.908 million. So right here, I think we said, hey, at this 99%, that means that 99% out of 252 is 250. Well, the 250th smallest loss is the same as the third biggest loss. So that meant that our value at risk was right here at observation number 3, at the third biggest loss. So now suppose we want to calculate the expected shortfall given this value at risk. Now my question to you is, what is the expected loss given that losses are bigger even than this 18.908? And for that I'm going to direct you to Mentimeter. So given that we have value at risk, what is the expected shortfall? I'll give you a moment to pause me. And then the answer is 25.243. So why is that? Well, which returns are lower than this loss of 18.908%? Well, there's only 2 of them. So if we then take the expected value out of these 2, simply the average of these 2 values. So easy enough. So one thing to note, value at risk is the loss level that you won't exceed with a certain probability, and then expected shortfall gives you some information about, hey, given that we exceed that level, what will be the shortfall. So theoretically, expected shortfall tells you more about, hey, what do you expect to lose, rather than, hey, what do I not expect to lose. So if you then want to make, let's say, certain capital requirements, these are equity requirements as the Bank of International Settlements wanted to do, then maybe expected shortfall is a better measure, because it tells you more about, hey, what do you actually expect to lose once you start losing money. And that's exactly what they did when the capital requirement calculations were based deeper into expected shortfall than in value at risk. So to close up this lecture, I wanted to talk a little bit about the shortcomings of the value at risk and how to solve those. So first of all, how do you know if you have a good value at risk number? Well, what you can do is do some back testing, right? Where you simply test, suppose I have a certain value at risk for 10 days, then we can ask ourselves, if we take 100 observations and we want to know this 99% 10-day value at risk, then we can see how often is this value at risk number exceeded. Well, if I have 100 observations and it's exceeded once, then, well, I have pretty good value at risk model. To visualize that, so suppose we have here a certain value at risk. So we see this number, that's the blue dotted line. This number changes over time because, well, we lose money, we gain money in our portfolio. So the value of the portfolio changes over time, which means that also the value at risk changes over time. And then if we compare what actually happens in terms of the gains and losses and compare that to the value at risk, we can see how well the model does. And so here I see this is a 95% one-day value at risk. We have about 50 observations, so for 95% over 50 days, I would expect that the value at risk is exceeded, say, 2-3 times or so. And if I look at the data, it's exceeded once, twice, and here maybe 3 times. So it looks like this value at risk is doing pretty well. What I can also do is, if I want to, rather than testing from data from the past, I can also do some scenario analysis where I put in some certain assumptions on the data. So let's say I want a higher unemployment rate or a higher GDP growth or more extreme versions of certain debt crisis or so. And then simulate, hey, what happens to the value of my portfolio. So one way to do that is through Monte Carlo simulations, where you simply take some inputs into a model and then run a simulation 10,000 times or 100,000 times or 1,000,000 times, depends on how much computing power you have, and then look for, hey, what is the actual outcome that I find? Is this outcome from these Monte Carlo simulations consistent with this 99% cutoff point for my value at risk, or is it more consistent with a 95% cutoff point, or whatever you want to test for. So one problem with doing some scenario analysis that falls within, let's say, normal normal occurrences, then the problem is that you will never find very extreme losses. Also not if you look for historical data, because, well, even though you have these extreme losses that do occur, they're not really either in the confines of normal assumptions for a model, nor are they usually found in the data. So suppose you take data between, let's say, 2009 and 2020, then you will find that the variance is pretty low. But then once you start including, let's say, 2008, or you include 2020, all of a sudden you find the Corona crisis or the 2008 financial crisis, and all of a sudden you find these tail end events in your data that are not part of normal modeling of these events. So how do we deal with these fat tails, right? And there the answer is, do some more scenario analysis in the terms of stress testing, and there's also a branch of theory, extreme value theory, that you can look at. So stress testing is more or less scenario analysis, but now rather than putting somewhat normal events in your scenarios where you say, hey, I'm going to look at what happens if the unemployment rate goes up by 1 percentage point, or what happens if GDP falls by 0.5 percentage point, or something like that. You put in some very extreme scenarios in a scenario. So for instance, you put in stuff that makes it look like the 2008 financial crisis, what's the data that's consistent with European sovereign debt crisis, data that's consistent with what we have now with the Corona crisis. And then look for, hey, what happens to the value of my portfolio under those extremes. And that can be very useful to see, hey, how well do these banks actually hold up? Do they have enough equity to make sure that these losses ensure that the assets are still worth more than the liabilities, because otherwise they're bankrupt. What you can also do is pay more attention to what happens in the tails, and that's a branch of statistics called extreme value theory. I am slightly familiar with it, but not too familiar. So if you really want to know more about this, you'll have to go deeper into statistics, and likely you will even have to start doing some econometrics, or maybe even go to Tinbergen Institute after your master's to delve deeper into, hey, what is extreme value theory? But extreme value theory kind of gives you an idea of, hey, what do you think would happen in the tail? So the normal distribution, normal statistics is mostly concerned in, hey, what happens in the bulk of the observations, and so what happens in the mean, around the mean, within 2-3 standard deviations. That's the stuff that we're interested in, because that's what happens most of the time. Extreme value theory is not like that. It doesn't care at all what happens in the middle of the distribution. It only cares what happens in the tails. And then in these tails, well, there it starts modeling, so what happens. And well, then maybe more extreme stuff starts happening than you would expect based off simple normal distributions. I'm by no means an expert, so I did some stuff on this in grad school, and I had a moderate amount of fun. So if you're interested in this stuff, I can maybe point you towards some other courses that you can take to delve deeper into this. But for me, my knowledge is kind of limited in this area. And the same goes for, well, this subject where like extreme value theory, where you're interested in, hey, what happens in the tail, you can also make some assumptions on what happens to the correlations in the tail. Because normally, if you think about correlations are linear, so that you simply take data out of an entire distribution and then check how correlated is this data. But what you find in practice is that the correlation is not linear. Well, maybe it's linear for any normal observations, but then in a tail, you may find that correlations all of a sudden increase tremendously. Yeah? So, for instance, think of the latest financial crisis, when before the financial crisis of, let's say, the subprime mortgage crisis in the United States. Before that subprime mortgage crisis, let's say mortgages returns in California, New York, Chicago, and Texas were not that correlated. Whether someone defaults in California may have to do with the Californian economy, but that's more or less separated from what's happening in Chicago, Texas, and in New York. But then all of a sudden, during the subprime mortgage crisis, all these mortgage returns, they were suddenly highly correlated. Everyone defaulted all at once. And what you can do is start making some assumptions about how big is the correlation in the tail, so that the tail behaves differently from the normal distributions. So you make a so-called copula, wherein your correlations are not linear anymore, but can take any form. So again, a bit beyond my knowledge, because, well, I'm not a statistics guy, nor am I an extreme value guy. But if you're really interested in this, maybe I can point you towards someone who can tell you more about this, or where you can find courses to learn more about this. So that kind of concludes our little escapade into value at risk and expected shortfall. So once again, I wanted to talk about this because if you're going to do anything in terms of risk management, which is not completely unlikely given that you guys are studying economics and business economics, I wanted you to at least be familiar with these terms, so that when someone from the risk department is talking to you, that you know what they're talking about. So value at risk, certain level of losses that won't be exceeded with a certain percentage of certainty, and expected shortfall, what happens, what is the loss given that this value at risk is exceeded. We talked about how to estimate this from data, how to get value at risk from a normal distribution, and we talked a little bit about, hey, what's good and bad about using data versus using some more assumptions on the distribution. And finally, we talked a little bit about tail end probabilities. So next time I'm going to talk about CAPM, the weighted average cost of capital, and multi-factor models of risk. Hope to see you there.